Hello everybody. So I think people are joining in, so we'll give maybe a couple of minutes, but as we wait for a couple of minutes, I'll go through a few things. So thanks everybody for joining. So we have exciting session today. This is actually a AAEA track session that was supposed to be he was supposed to be in New Orleans in the meeting, but we couldn't make it for various reasons. So then we moved it to virtual session here, and I'm glad we did that because we have a lot more attendees that way. So we have three exciting presentation and plus a discussion today on groundwater and sustainable development in South Asia. And I'm Kashi Kafle, Texas A&M University, and I'm organizer of this session, and this is approved by AAEA International Section. Couple of housekeeping things before we move to the presentations themselves. So we have like I said, we have four exciting talks. So we start with Dr. Disha Gupta. She will talk about pricing farm electricity and water use efficiency, the case of India, Punjab. And then we'll go to Dr. Mary Charlotte Buisson. She will talk about the solar irrigation from Bangladesh, and that's co-benefits of solar irrigation. And then we go to Dr. Ram Fishman, and he will talk about the groundwater capital and accumulation of man-made capital. I think that's the case from India and Nepal. And after this, each of these three presenters will have 15 minutes to present, and followed by 5 minutes question and answer. Then we move on to Dr. Soumya Balasubramania. She will discuss these three presentations plus other overarching points about these sustainable development and groundwater irrigation in South Asia for about 15 minutes. And if time permitting, we'll have another round of question and answers at the end. So a few things, please mute your microphone unless you're speaking, and use the chat function to ask questions at any time. You can just, and then I will try to moderate them and direct them to the presenters after the presentation is over. And you can also ask questions during Q&A session, like each presenter has 5-minute Q&A. And if you want to do that, please raise your hand, alert me, and I will let you speak, ask your question, time permitting. I cannot guarantee everybody will have time to ask question that way, but please make sure you, if you want to ask question, use the chat function. That's the best way. But there will be some time for oral question as well. So with that, I will start up, and then I'll let Disha please share your screen, and floor is yours.
Thank you very much, Kashi, for organizing this session. And thank you very much, everybody, for joining in today. I'm Disha Gupta from Indira Gandhi Institute of Development Research. And today I'll be presenting on pricing farm electricity, water use and efficiency, the case of paddy cultivation in Punjab. This is a paper which is based on one of my dissertation chapters, and your comments and suggestions are very welcome today. Okay, so India is the world's largest user of groundwater for irrigation, and among all the states, Punjab is doing the worst in the sense that the annual groundwater extraction with regard to the natural recharge is, about 166%, which is highest as compared to any other region in the country, according to the estimates given by the Central Groundwater Board. And some of the key factors that are contributing to over extraction of groundwater resources in this region are believed to be the policy of free farm electricity and cultivation of water intensive crops such as paddy. Since this is an international audience, I just thought of showing what the area of study is. So, that's the map of India, and here in red is marked the state of Punjab that we are talking about today. So, this graph shows you how the cropping patterns have changed in the Kharif season in Punjab over the years. Notice that in the 1970s, there was substantial area under maize and cotton cultivation shown by the red and the green bars, whereas, over the years, the area under paddy cultivation shown by the blue bars has gone up substantially. While I was telling you that there are several reasons for, these changing cropping patterns today, I am going to focus on the pricing of the farm electricity. Now, the policy of free farm electricity was introduced in the state in 1997. So farmers are really not paying anything for using of these resources. And that's the reason that they do not have an incentive to use them efficiently, which contributes to their depletion. And what has happened also over time is that the use of electric operated tube wells have gone up, and so have the average groundwater depths in the state. So over the last 4 decades, the average groundwater depths have, almost become 3 times. So, while, there are several studies that highlight that policy of volumetric pricing may not be politically feasible and that may harm farmers, especially the smaller farmers. Today, in my work, I'm going to attempt to show you a policy framework which involves pricing of farm electricity and also cash transfers to the farmers in order to keep their welfare unchanged. So broadly, there are 2 objectives of my paper. The first one is to estimate the reduction in water pumping under volumetric pricing of farm electricity in the state. And how I'm going to do this is that I would be estimating a production function for paddy cultivation in order to get at the estimates of marginal productivity of water, which will help me quantify how the water volumes and yields are changing when there is a change in the price of electricity. And notice that, when that happens, there will also be an adjustment in the quantity of other inputs and paddy yields. And secondly, I would be also quantifying the lump sum transfer that's required to keep the welfare of the farmers unchanged. And I'm going to show you how you could go about financing this. So coming to the data sources, the first one is the cost of cultivation data. This is, the primary source of data, and the cost of cultivation surveys are collected by the Ministry of Agriculture using a 3-stage stratified sampling design. It's a 3-year rotating panel data set at the level of plot, and it gives data on output produced and various inputs such as labor, machine, irrigation, hours, etc. And that's both in physical as well as monetary units. Now, this part of the data is publicly available. Then there's also irrigation hours by pump type and horsepower rating of the pump. That's not publicly available and has been requested from the ministry. So my sample consists of 504 parcels on which 238 farmers are cultivating paddy in at least one of the 3 years. And this is the block year that I consider in this analysis. So the second source of data is the Central Groundwater Board data, which gives you data on water depths, which are recorded for 4 times in a year. It also gives you the GIS coordinates of these test wells for which the data is recorded. And finally, I would be using the rainfall data from Matsura and Wilmot, which is a GIS gridded data set with resolution 0.5 by 0.5. Total water use is one of the major variables that goes on the right-hand side when I'm estimating my production function. Now, how I've computed this, I've included water from all the sources, including groundwater extraction and rainfall. But note that here, I'm not considering canal irrigation or conjunctive use of canal and groundwater, just because, I don't have measurements for canal irrigation from this data set, although I do have data on canal irrigation charges, but, they're all zeros and uninformative. So this is the formula that I use for computing the groundwater extracted. This is nothing but, the formula for energy, which is power applied over time for extraction of water. So, lifting any mass against gravity would require energy, and that's what this formula is. So over here, IJT is the mass of water extracted on parcel I, tehsil J, and near T. Acceleration due to gravity, that's the groundwater depth at the tehsil level. This is the efficiency of the irrigation pump, the horsepower rating of the pump, and the irrigation hours. I have taken several assumptions around the efficiency of the pump type, and in the interest of time, I'm not going into details of it, but the efficiency of a diesel pump is taken to be the lowest, and that of submersible electric submersibles are taken to be the highest, although I've done a sensitivity analysis by changing the efficiency of the pump, and I'll show you that the estimates remain pretty similar. Then I have estimated the tehsil level rainfall by taking a weighted average of the grid points that lie within 50-kilometer radius of the tehsil center, and combining these 2 numbers, I get the total water use in cubic meters per hectare. So these are the summary stats from the sample that I have. Note that the average paddy yields are 65 quintals per hectare. The average crop area is 1.75 hectares. Now this is, higher than the national average. I also want you to keep in mind that the average water use is about 38,000 cubic meters per hectare, and the maximum comes from the submersible pumps, which is not a surprise in a region like Punjab, where the depths are higher, and thus most of the farmers are using submersible pumps. Also, I must say that, farmers in Punjab have a unique feature that, they are pump owners and they're large farmers, so they're rich farmers in general. And coming to the horsepower rating, the submersible pumps are the most powerful with an average horsepower of 12 HP, followed by diesel, and the lowest for the non-submersible electric pumps. So also, as I was saying, that, on maximum parcels, there's electric submersible pumps that's used for irrigation, and, followed by electric non-submersibles and diesel. So moving to the production function estimation, there are econometric issues pertaining to the estimation of the production function. Input used by farmers is a choice variable which depends upon several factors such as quality of land, elevation of the parcel, etc. And while these factors are likely to be observed by the farmer, they are unobserved by the econometrician, and thus they are a part of the error term. Now, input use and error term might be correlated, and thus, our inputs are endogenous. Now, panel data allows me to take care of the time invariant unobserved heterogeneity. I have used the parcel-specific fixed effects for that. But there still might be some omitted variables that vary across both space as well as time. And in order to deal with that issue, I use the instrumental variable approach. I would be using the input prices as the instruments for the inputs on the right-hand side. So from the input demand function, we know that there is a negative relationship between them. But before I speak a little bit more, let me show you the specification that I use. Although I began with the translog specification, the larger order terms, which is the square terms and the interaction terms, were jointly insignificant. So I chose the Cobb-Douglas specification. So the instruments that I have are input prices, which is casual labor wages, hired machine rent, own irrigation charges. And additionally, I also have groundwater depth being used as the instrument for water. Again, there would be a negative relationship between water use and water depth, because higher the water depth, higher would be the unit cost of water extraction, and lower would be the water use. So let me skip through the first stage regression, although, I have some more on the right-hand side. Apart from labor, machine, water, and fertilizer, I also have insecticides and seeds. Let me show you the FEIV regression just in the interest of time. Here, the first three columns are the first stage regressions, wherein labor, machine, and water are taken as the dependent variable. I also must say a few words about fertilizers. I've assumed that fertilizers is exogenous over here because fertilizer uses according to some schedule given by the government. So that's taken as exogenous. The fourth column in this regression table shows you the production function estimates that I would be using for estimating the marginal product of water, and also for doing the simulations. So so what I do over here is that, I estimate the marginal product of water for all the plots, and this is just the Cobb-Douglas function in the exponentiated form, and it's differential with regard to water. So the average marginal product of water is 0.34 quintals per 1,000 cubic meters of water, or about 34 kilograms per 1,000 cubic meters of water, which is quite low. And let me just show you what I have in terms of the diagram when I really plot all the marginal products of water. So the function is convex as one would expect, but this is relatively flat. And also at the average water application, which was about 38,000 cubic meters per hectare, this is, completely flat, which means that with additional units of water, the output would go up by only very few units. And so, we are going to use this when we look at simulations. So finally, I do simulations wherein I see what happens to groundwater use when there is pricing of electricity. So here I'm assuming that farmers are profit maximizing agents, which means that the unit cost of water under free farm electricity is estimated using this equation where, CIJT is the unit cost of water, PT is the price of Paddy, and MPW is the marginal product of water. So from here, I get the unit cost of water. Now, for every incremental increase in the price of electricity, there would be an incremental cost of water extraction. So, let me just give you an example. So, for example, if the price of electricity increases by ₹1 per kilowatt hour, for a 5 horsepower pump, this would be roughly equivalent to ₹4 per hour for extraction. And thus we could see what is the incremental cost per hour. And we also know from the initial bit that how much of water is extracted every hour. So one could find out the incremental cost of extraction of water per cubic meter using this and the production function estimates. one gets what happens to the water use, to the other inputs, to the paddy yields, and to the profits of the farmers. So just to put it more clearly, let's say that the unit cost of water goes up from, so initially the unit cost of water was C, so our equilibrium was at this point, so the water use, the average water use was W. Now the unit cost of water goes up to C prime, so there is a reduction in the water use. Simultaneously, what's happening in the other input markets, over here I'm just showing you labor, but that's true for machine, fertilizer, etc., that your value of marginal product of labor, machine, fertilizer would shift inward, so that there would be a reduction in the input uses, and thus there would also be a simultaneous inward shift in the VMP of water. And so the reduction in water use would be much higher when all the inputs adjust, given the structure of the production function that I have. Thanks, Kashi. That's sufficient. Thank you very much. So when you increase the price of electricity from 0 to ₹5, and ₹5 is the average cost of provision of electricity in the time period of study, what really happens is that my water use goes down from 33,000 cubic meters to about 8.6 thousand cubic meters, which is roughly about a 72% dip. Also, notice that there is a decline in the average paddy yields from 65 quintals per hectare to 45, which is about roughly a 30% dip. There is also a decline in labor, machine, and fertilizer of about 30%. Now, this is under the assumption of the pump efficiencies of 25, 40, and 80%. Let me show you what I have if I change these pump efficiencies. Let's assume that I take pump efficiencies wherein all pumps are 25% efficient, all are 40% efficient, and instead of taking the efficiency of 80% of submersibles, let me bring it down to 50%. Even then, notice that the dip in groundwater use is much sharper than the dip that you see in the paddy yields, and this is not a surprising result given the shape of the marginal product of water that I showed you a few minutes back. The other thing that I want you how much is the dip in the profits? So if we just look at the specification that I showed you, there's about a 10,000 rupees per hectare decline in the farmers' profits. And that's, close to that is how much the state electricity boards would be gaining by pricing electricity. So one could actually use the collections done by the state electricity boards in order to give back to the farmers for keeping their welfare unchanged. Again, the results are qualitatively pretty similar, even if I change the efficiencies of different pump types. The final thing that I want to say while wrapping this up is that, once there would be also a reduction in the other input uses, something that I'm not showing in the study is that whatever resources are freed up from paddy cultivation could actually go to cultivation of other less water intensive crops. So there also might be some crop diversification happening when we are pricing electricity. There are a few limitations in the way I've computed this because I have not adjusted for several things, such as, I don't even take into account the adjustment in the MSPs, but notice that when the cost of cultivation really goes up, there would be, increase in the MSP, and thus the revenues of the farmers would increase. So this somewhat gives us the lower bound of the reductions that I'm showing you. So yeah, thank you very much. Thanks a lot for your attention. I'm open to questions.
Thank you, Disha. You're right on time. So we're open for questions, please. If you can raise your hand, Zoom hand, and unmute, ask questions, or also you can send questions in chat as well. We have 5 minutes for questions and answers.
Hi, Disha.
Hi.
Thanks for your presentation. Yeah, just a quick one. I'm just wondering why, or maybe let me put it elsewhere. Is there a reason you have not also explored the flexible functional form, the translog, in addition to the Cup-Douglas? Or maybe your prior test was pointing to just only the Cup-Douglas and not the translog. You probably should look into it. And then also, there's a lot of work also done within the framework of the stochastic production frontier functions. Mm-hmm. And I think with production, it's the reason to actually examine both, the exogenous factors that can be attributed between actual inefficiency and then something that's also stochastic to the farmer. It's also, you should look also into that, how best to articulate that within the production, the stochastic production frontier framework. Thanks.
Thank you very much, Eric. I did try out the translog production function. Possibly I was too quick because it's just a 15-minute presentation. So the problem with the translog is that the higher order terms were, sort of insignificant, were jointly also insignificant, and, there was nothing in there when it came to the translog. I did not put in the table here, but I do have an additional table in the appendix of my paper. I would be happy to share it with you, but thank you for the comment on the stochastic production frontier. I will definitely take a look at that.
Awesome.
Thank you.
Good job.
Could I ask a question? This is Keith Fugley from USDA. Your results seem to indicate that as water use falls, the use of all these other inputs is also falling. And I would have expected to see more substitution of possibilities, particularly with the Cobb-Douglas production function, that you could see some of that being offset by increases in other inputs. I wonder if you could just talk about that.
Right. So somewhat some of the results that I show you may look like an artifact of the functional form that I have assumed over here. Given the Cobb-Douglas, it's bound to happen that with a reduction, there would be a reduction in the other inputs as well. So, that's the reason that I started off with a translog. But yeah, I would be happy to take suggestions on some alternative techniques that one could be using here in order to, already estimating a production function is quite a challenging exercise, as you see, given that there are multiple inputs and, there are multiple things involved here. I would be very happy, to hear out the suggestions on how to better this estimation.
We have about 2 minutes.
Ram has a question in the chat, I think.
Yeah, there's a question from Ram. Can you see the question, Disha?
Yeah, can you give us an idea of the share
I can read it for you if you want.
expenditure were it to be priced of
Yeah.
the farm? Well, Ram, that's a very good point. I don't have that number on the top of my head, although at zero, pricing of electricity, irrigation expenditure is about at 14%, the maintenance costs, etc., comes out around that much. And I'm sure when you price it at 5, the share of irrigation goes up quite a bit, but I'll make sure that I answer that question for you maybe later. But thank you very much.
Thank you. Thank you. Very interesting.
We can probably take one quick question if anybody has one quick question. We have like about 30 seconds. All right. So I think, okay, there's one question. In the chat, there's Rio asked, did you have the explanation of type of irrigation that use groundwater?
By the type of irrigation, do you mean the type of pump? You could unmute yourself, Rio. Oh yes. So, basically, Kashi, let me just take a minute to, maybe 30 seconds to answer this. I know I skipped many things over here. So, there are majorly 3 kinds of pumps that are used in Punjab: diesel, electric submersibles, and electric centrifugals. Now, the diesel pumps and the electric centrifugal pumps are actually surface pumps, and they operate at very shallow depths of about 8 meters, while, submersibles are capable of operating at quite deeper depths. And that's the reason, farmers are forced to use submersible pumps, because the average groundwater depth in this region is very, very high. This actually reminds me of one of the papers by Sheetal Sekri, which talks about, how the pump technology changes at several groundwater depths. I would be very happy, Rio, to share the work with you. I'm sure you'll find it interesting. Thanks, Kashi. Thanks for giving me that much time.
Thank you, Disha. Thank you very much for sharing your presentation. So now we go to Dr. Mary Charlotte Buisson. Please share your screen, and the floor is yours. We have 15 minutes, and I'll be alerting you when you have 3 minutes to go.
Okay, all right. Can you confirm that you're seeing my screen?
Not yet.
No, so I need to do it again, sorry.
Yes, something is coming. Okay, I can see it now.
Yeah, okay, I think that's fine now. All right, so thanks everyone for being there and attending this this session, and thanks for the organizers. That's also good to have that online and to see that large audience being there. So what I'm presenting today is an article based on work that we have been doing in Bangladesh around solar irrigation, and that's titled "A Place in the Sun: Farmers' Co-Benefits from Solar Irrigation in Bangladesh." So the context in which we are working is that of energy transition in agriculture, and especially in South Asia. So many of you in that call may already know that South Asia food systems is highly dependent on groundwater, and that's also support the food security. Simply taking Bangladesh, India, Nepal, and Pakistan, we estimate that the food security is supported by about 21 million of irrigation pumps. Some of those being operated by electricity, as Disha presented for the case of Punjab, and other being operated through diesel power. Diesel power use simply means very quickly carbon emissions, and those can be quite high. We have, for example, estimates in India, which account for 4 to 11% of the country's total emissions simply coming from irrigation and diesel use in irrigation. And on the other side, we have the international commitment with the indices, which have been including solarization of irrigation in the indices for many of countries in South Asia. Because of this framework and really solar irrigation starting from the energy sector, we see that the solar irrigation programs have also been designed and implemented by the energy sector. But at the same time, we see that most of these programs are still highly subsidized, and even in more successful settings, they still struggle to demonstrate their financial sustainability. So that's the bit of the context. And what we bring here is the lens of the co-benefits to look at the impact of the SIBs. So what do we mean by co-benefits? We simply use the definition coming from IPCC, where we consider co-benefits being positive effect that a policy or measure aimed at one objective initially, in that case, mitigation of carbon emission, might have on other objectives, and thereby increasing the total benefits for the society or the environment. So in bringing this co-benefits lens, we are actually breaking the silos, which are related to the implementation and the financing of solar irrigation. We do bring and help to think about synergies between climate change mitigation and SDGs. And we kind of also localize the impact, because that's not anymore only the social and global impact of solar irrigation in terms of mitigation, but that's also the local impact for farmers and adopters. So the research question we worked through with this analysis is, first of all, beyond the objective of mitigation, what are the co-benefits of using the SIP for the farmers? And more specifically, how does using a SIP impact the household level and the farm level outcomes? And then we'd also explore the pathways which explain these outcomes. So a bit more details about the water, food, energy nexus in Bangladesh. We'll talk a lot about borough paddy cultivation. So knowing that irrigation is really the backbone of the agricultural sector in the country, actually the growth in the food grain production, and therefore the progress toward food security has mostly been supported by the rising production of water-intensive dry season paddy, which is the borough paddy. In Bangladesh, the dependence on diesel pump is also quite important. We estimate that there is 1,043,000 diesel pump in the countries, which do present some risk for the farmers in terms of price fluctuation, but also at the national level with an overloaded balance of payment due to the import of diesel. And that's that use of diesel also contributes to the emission. I won't come back on that. And at the same time, at the national level in Bangladesh, there is quite a high ambition to transition towards solar irrigation. So there are a number of targets set up in the policies. And interestingly, in June 2023, the then Prime Minister instructed the officers to take steps to power all the irrigation pumps in the country with solar energy. So that was quite a big announcement. Not realistic in the short term, but still showing the ambition. All right. So still to get you into the context and exactly what we are talking about when I talk about solar pumps in Bangladesh. The case of Bangladesh is a bit specific for solar irrigation because the model which is mostly implemented and mostly in place in the country is a fee-for-service model. So in that space, there is an institution, IDCOL, who would provide grant and loan to sponsors. And those sponsors are either NGOs or small and medium enterprise who will be paying also a 15% equity. And then those sponsors will be operating the pumps through selling water to the farmers. And the farmers will therefore pay an irrigation fee to the sponsor, and the sponsor will pay back the loan. So that's a bit of an outlier on the space of solar irrigation in South Asia because of this fee-for-service model. And with that system in place, I simply put that picture so that you visualize what we are talking about. We are actually talking about a relatively large system with an average capacity per SIP of 28 kilowatt, and therefore serving relatively large command area. So that's about 18 hectares. And that simply means that it's about 50 farmers who are being served on average during the dry season by a solar pump. So that's the system that we talk about. All right, so let me coming back to the framework and to what we actually looked at with this analysis. So we try to understand how the access to SIP actually have impact on the farm level outcomes. Here we mean the yield, the profitability, and the agricultural outcome, as well as on the household level outcomes, the food security, diversity, the wealth, and potentially the income. And obviously those different outcomes are interlinked one with each other, as you can see from here. And once we establish this, the next step is simply to look at the pathways and to try to understand why we see this result. And we'll investigate three pathways, actually. So the first one is the pathway A with the irrigation practices. So here the assumption is that once farmers have access to solar irrigation, they may change their irrigation practices, be it in terms of the number of irrigation, the duration of the irrigation, or the quantity of water that they are applying to their plot. And this may have an impact on the yield. So that's the first pathway. The second pathway is through the input use and the cost. So here the assumption is that once there is a change in the production function on the irrigation input because of the change in cost, that may have implication on the use of this input or the use of the other inputs as well. So a change in the production function for the inputs once one input is changed. So that's the second pathway. And the first pathway is a change in time allocation. So here the assumption is that once farmers are spending less time on irrigation because they have access to the SIP service, they may allocate more time on other tasks and other generating activities, and potentially with an income effect. So that's the three pathways that we'll be looking at. Okay, so we use data collected in 2021 in Bangladesh with a representative sample of SIPs being in northeast of the country. We have a sample of 900 households coming from 60 villages. Out of these 60 villages, we had a design with 20 treated villages, 20 pipeline villages, not treated in 21 and which became treated 2 years later. And finally, a sample of 20 control villages, which were selected by matching with the pipeline villages. At the village level, the selection of the household was through stratified random sampling, and we had 15 households in each village. So that's what we had. Well, simply to add that since then we had a follow-up survey, but this analysis only used the data collected in 21. All right, so because we are using the data from 21 only, we are using a probability score matching to account for the non-random access to SIP. So we use a model of treatment that will use household and farm level characteristics, village characteristic, as well as plot characteristics to explain the treatment. And then we do the matching using the propensity score, which is the probability of access to SIP, both at the household and at the plot level. So there are two levels of treatment depending on the outcomes that we look at. And then we'll use different methods of matching. I'm presenting the result for the nearest neighbor matching, but we also did sensitivity analysis with different caliper, different number of neighbors, and we also did some robustness check with the weighted OLS. I'm not going through the tests, so the purpose is just to tell you that we put all what we could, and yes, that's in order on that front. Okay, so let me coming to the results. And I'm starting with the effect of SIP on the household level outcomes. So here our variables are the food security and the poverty. And what we are seeing is that on average, the household with access to and use of solar pumps reach a food consumption score, which is higher by 4.4. And that's actually equivalent to 25% of the standard deviation. So not a trivial number. And then through the adoption of SIP, we also see that the household can diversify their food consumption, because that's again about one category of food item which is added to the food basket for the SIP user. So that's the result that we have on the household level outcomes, and especially on the food security and diversity. Second, still on the result, we are looking at the farm level outcomes and the cropping patterns. And here we see that the SIP users tend to be less diversified than the non-SIP users. And their cropping intensity is also negatively influenced by their access to SIP. And this simply happens because the SIP adopters—
3 minutes, Marcel.
All right, the SIP adopters allocate 6% more of their net crop area to the dry season paddy. So they spend more of their cropping area on burrow paddy cultivation. On the profitability, we also see that the profitability is significantly higher for the SIP users as compared to the adopters. That's again quite an important result, because the average gain is equivalent to 25% of the mean. So that's again quite important. I'm running a bit to give you a flavor of what we're finding with the pathways. First of all, on the irrigation practices, what we are seeing is that the number of irrigation provided to the crop throughout the season is not influenced by the SIP. We don't see a significant change there. But what we are seeing is actually a change within the season. So the time the crops get irrigation is different. So that's also something very, very interesting, because potentially that may mean that the quantity of water which is applied to the plot is not different, but the time when the crop has access to irrigation is slightly different, and hence this may explain something on the yield potentially still. On the pathway B and the reallocation of the inputs and costs, what we are seeing is that the cost of labor and the irrigation costs are lower for the SIP irrigated plots. I would say that this is that was an expected result. But what we are also seeing is that the kind of into bracket saved cost of irrigation is not necessarily reinvested into other inputs. So the production function is not being changed so much. And looking at the last pathway on the change in time allocation, we indeed see that the SIP user are spending less time on irrigation. Again, quite important, because that's 50% of the mean less time. But we don't see any impact on the time spent on other activities on farm or off farm. So again, maybe what is saved during the peak season is simply not enough to still start a new activity and get income from this new activity. So quickly wrapping up, we have three main findings. So positive, significant, and robust effect on the household security and dietary diversity. We do see that SIP is associated with less diversity in the cropping pattern and higher share of the cultivated area being planted with burro paddy. And we see that the SIP irrigation positively impact the profitability again of the dry season paddy and of the farm. The transmission channel, we have mostly identified the lower cost of SIP irrigation and the lower cost of labor as being the transmission channel to explain those results. Just to explain why those results are important, and again, to bring that back to the lens of the co-benefits, we did some back of the envelope calculation. And what we are saying is that really saving on emissions, if we value the saving on emissions on carbon emissions, that's about 500 USD per year per SIP. While when we do the same calculation with back to the envelope calculation from the farm profitability, actually we see that the SIP bring an average almost 900 USD per SIP, which is transferred to the farmers. So interestingly, once we are able to value the co-benefits along with the mitigation benefits of the SIP, that's potentially doubling the economic return of the SIP. So that's completely changing the landscape and the thinking on the finance of this intervention. Yeah, I'm done. Sorry for the time.
That's fine. You went over 1 minute, but that means we have 4 minutes for question and answer. So it's open for questions and answers. Any questions? Okay, so we have 4 minutes for questions. Please unmute yourself and ask questions or put in chat. As the questions keep coming, I will. I have one. I guess more of a clarification type of question. So the whole time I was thinking about the market access stuff, Marisol. When you were talking about the co-benefits, I think there is some implicit assumptions that you're making on market, right? So that people who produce things using, solar irrigation, they're able to sell and get fair price. Is that the assumption there, or is there something we can do? Maybe that probably the co-benefits depend on. It's contingent on being able to sell, I guess, right? So you're muted.
Yes, I think you're right, Kashi, and maybe we need to make clear that those results are valid internally for the specific case of Bangladesh, and we may need to have a discussion on the external validity. Simply also because the solar irrigation in the case of Bangladesh have been put in areas where there was already quite intensified cropping patterns toward burro. And hence what you are saying in terms of market access, the market is already there. So this is not necessarily about converting and getting access to irrigation. That's not about getting access to new crops because you get access to solar irrigation. That's not the picture that we worked on in Bangladesh. I think, yes, we need to make those assumptions very, very clear indeed. Yeah, thanks for that.
Okay. So we see some activities.
I had a quick question.
Okay, please.
MC, I'm just wondering, your survey was done in September 2021. I wonder how much of that increase in Boro cultivation could have been a result of just post-COVID lockdown and risk aversion in terms of diversifying and growing vegetables, etc., that people generally do. I mean, it's not uncommon in Bangladesh to see farms cultivate Boro one season and then the next season they're kind of doing vegetables, etc. But when you've just had a bit of a shock, and I wonder to what extent the results that you're finding might be somewhat influenced by that.
Yeah, that's a super interesting point. Thanks, Sumia. I don't think that we see a drop in burro cultivation during COVID in Bangladesh, but that can be rechecked again. Also, interestingly, since now we have the follow-up survey, what we are actually saying is that burro cultivation is not increasing anymore, while it was increasing in the previous year. But it's still increasing in the SIP areas. Yeah, that's what we're seeing.
Right, and you could, I mean, and potentially extensive margin cultivations could be such that you increase boro and do other things as well, right? So one need not
to some
happen at the
extent.
expense of another, no? So
yes, potentially yes. Even if you know that we are relatively close already to the maximum of intensity that we could of cropping intensity that we could reach. So this extension margin effect is not is not so much relevant in that specific landscape. Yeah.
okay.
All right, we have like 5 seconds. That means I think it's essentially over. Thank you, Marisela, for a good presentation. Thank you for sharing this with us. So we'll then move on to the third presentation. Ram, you're up.
Thank you. I'll just share the screen.
Yes, I can see your screen.
I'll try to go to full screen mode. Is it still visible?
Yes.
Okay.
It is.
Okay, great. So I want to raise a broad question about about groundwater use in India, which is whether it's really unsustainable, as we often hear. Obviously, there is a lot of concern about the fact that in many parts of India, including, as we have heard, in Punjab but other places as well, there is this widespread situation that is associated with overexploitation of the resource and declines in groundwater tables all over in many agriculturally important parts of the country. So there's tremendous amount of concern about where that will take Indian agriculture, and tremendous amounts of worry about the unsustainable nature of this endeavor. And that is all fair and true, but when we talk about sustainability and we think about it from an economic point of view, we also know that ever since the 70s, many leading economists have raised the question of weak sustainability that I'm sure everybody is familiar with, basically raising the possibility that depletable resources might be exhausted while the economy can still be on a sustained path of consumption. And we know the work of Solow and Hill, Gupta, Stiglitz, and we know Hartwig's rule, which formulated that under certain conditions, if the economy invests all the rents that are derived from the exploitation of the resource in other forms of capital, so in a sense substituting the losses in natural capital with gains or investments in man-made capital, then under certain condition of substitutability, et cetera, the economy can actually remain on a sustainable path even while those resources are being exhausted. And this is something worth asking in the context of India's use of groundwater, because for several reasons. I mean, it would be interesting to know whether, from a broad point of view of maybe development, the way the Indian economy has made use of this resource actually, is sustainable or not. We can ask whether it's efficient or not in a broader sense. And it's also relevant not only in a scholarly way, but not only because this process is still ongoing, but also because in many other parts of the world, there's a lot of discussion about that have not yet developed their groundwater economy, and that can include other parts of India, eastern parts of India. It can include sub-Saharan Africa and other places where there is concern about following a similar path to that taken by India. There's a lot of people are arguing that it's important to develop the groundwater economy, but it should be done in a very different way. These overexploitation needs to be avoided, that water tables must not decline, etc. But we do need to pause it for a minute, I think, and consider whether really that is as a policy prescription, we really need to be so cautious, because theoretically, at least, it might be possible that what India has done with groundwater has actually helped its overall development, and maybe is not as unsustainable as it may seem only on the basis of falling water tables. I'm not making that position. I'm not taking that position. All I'm saying is it's something that's probably worth thinking about. And so I would like to share with you some very, very initial and unsatisfactory attempts to try to look at this question empirically, okay? So from the onset, I want to lower the expectation. No conclusive answer at the end of the following 10 minutes, but maybe just first steps towards like thinking about that question. So it's obviously a very difficult question to ask, to study empirically. Because there are so many ways in which those rents from groundwater use can be invested, and it can happen through many channels. It can happen at the government level, nationally, right? If the country benefits from, let's say, reduction in food prices, or that is something that it can then also invest as at the national level, or it can happen at the local governance level, at the state or the district level, and it can also happen at the farm level, where farmers themselves who are benefiting from the use of groundwater might be investing it at the household level. And those investments can be made in very different types of capital, starting from physical capital, infrastructure, and also human capital. And perhaps human capital is the most interesting to look at because, you know, we think of it as a very essential component of a diversifying economy. When an economy is diversifying and moving away from the farm sector, the human capital is very much needed in order to enable the labor force to diversify to other activities. So perhaps that is one of the key forms of investment we should be looking at as something that can enable the Indian agricultural labor force to move away from farming as the resource gets depleted, and irrigation becomes more costly to implement. So here we are going to make some very initial attempts to look at this question through the channel of households. To what extent do we have evidence that farms that have benefited from groundwater irrigation over the last few decades have really accumulated higher levels of physical or human capital? We are going to be using data, microdata from both the census and the NFHS and basically just ask to what extent do we have evidence that where groundwater use has been more extensive, we also see higher levels of accumulation of these types of capital. And I'm going to describe two attempts to you to do that empirically. The first attempt is very much descriptive and therefore suffers some serious potential biases in the association we'll uncover. But basically, the first attempt just says, okay, we know in each district in India, you know, going back to the 60s, how much of the area was irrigated with groundwater in every year. We can take that, total it up over all the years, accounting for the crop mix and how much water that crop mix is supposed to take. And we can kind of calculate and estimate something like how much groundwater has roughly been used in every district over the last 40 years. And the result is kind of this map, which should be familiar to everybody. Maybe the color scheme is opposite from where it should be because blue indicates a lot of water has been taken and red indicates not so much. But that's basically, you know, a map we're kind of all familiar with. And that is a working paper with Howard Tobochnik, Anisha Zaveri, and myself. And then we basically just take district level data on present day capital stocks and just check for correlations. That's simple. And for some things, we'll see very strong correlations. So if we look at tractors as one form of asset or capital holdings, you can see, so each dot in the scatter plot is a district. The states are colored differently. And we see that in places, on the x-axis, you see the average amount of water extracted per year, okay? With 1 meter being very extensive, that's like probably where most of the places where Disha has been working. And we see, sure, they have more tractors, but that's very incomplete because tractors is an agricultural asset and it's also a complementary asset to irrigation. So that may not be that surprising. We can also look at other types of assets. Here are the percentage of households with bicycles, also seems to be well correlated. But when it comes to human capital, here we look at men height. And the reason we look at men here is because there's an issue we have to keep in mind here. We assume that the person we're observing has resided where the groundwater has been exploited. So most men actually reside where they were born, at least in rural areas, whereas most women migrate into those places. So that's why we are focusing here on men. It's easier for us to attribute. And here we see that it's not so clear that there is actually association with human capital, and the same goes for the literacy rate. Doesn't look like there's any clear association with the amount of water that has been extracted. In terms of a summary, here you see just a plot of the estimates that you get if you run these as regression with state fixed effects. So tractors are positively impacted, scooters also, mobile phones, most assets, refrigerators are positively associated where groundwater has been used up. And that also goes for, there are less poorer people and more wealthier people in terms of the asset index. In terms of human capital, it's a little more mixed. Again, we show results for females here. They're not very precise, not very conclusive, but again, focusing on males because of the migration issue. We do see some indication of men being higher where groundwater has been exploited. And we also see some indications that collecting data on school grades from across the country, that children are doing better in math and in reading in places that have exploited more groundwater historically. So a mixed picture, some indication that there is some association with higher accumulation of wealth and even educational human capital and height. But of course, the main problem with this approach is it's very, very prone to endogeneity. It's very hard to argue that access to groundwater has been exogenous. And so our second analysis attempts to look at that, and that is an analysis that led by Mathilde Dejoie, who is here in the audience. And there, what we're trying to do is, once more, trying to use geology to instrument for groundwater. Not the first time anybody's ever done that, of course. But the idea here is to look at endowments of groundwater that are based by geology and compare actually villages or households that are located in the same district rather than across districts as we have just seen, but in the same district, with the only difference between them being that some are located in areas with more alluvial aquifers with more water storage than others. So let me explain what that looks like. So if you look at the left map of India, this is a map that divides India into broad categories of aquifers, with the blue being alluvial aquifers, which are basically just big piles of mud, if you will. They store a lot of water. They dominate the Gangetic Plain, but they exist in many other parts of the country. Whereas the red areas are aquifers which are more shallow, and they tend to be more hard rock. The green and the red, they're complex hard rock aquifers. Oh, they have more water in certain pockets, but overall they contain much less water. And so empirically here, we are just trying to exploit a very, very coarse differentiation between alluvial aquifers on the one hand and all other aquifers on the other hand, because it's quite clear that that's where the main first order difference in the amount of water that's stored in the ground is happening. So it's well known that alluvial aquifers contain much more.
You have 3 minutes.
Much more water than the other types of aquifer. And what we do, we take all the districts in the country that have both types of aquifers within them, and then take all the NFHS household level observations, which are painted on the right map in red dots. Okay, every red dot is one cluster, NFHS cluster, where we have microdata, and we compare within the same districts households that are overlying the aquifers with a lot of water to those that have less water. What do we find? First of all, the first stage shows that indeed they actually practice more irrigation using census data. But more interestingly, also we see there is a clear effect on wealth. It's not huge, it's about 0.05 standard deviation in wealth indices, but we do see some accumulation of health. When it comes to human capital, it's a little more nuanced. We do see an effect on education, similar magnitude, both for women and men, more years of education, more weight, but not necessarily more height. Another exercise we do is also to remember that, not all of these districts are actually irrigated by groundwater. So we only expect the effect to come at those districts that are most irrigated with groundwater and not in those that are most irrigated with canal water. And indeed, when we look at those interactions, we see most of the effect is coming from when we interact the treatment, meaning being over the alluvial aquifers, with the extent of groundwater irrigation in district, consistently with the hypothesis on what's driving it. We see most of it is coming both in terms of wealth and in terms of human capital coming from those districts which are really groundwater irrigating. So just to conclude, this very, very initial step in addressing what is arguably an important question, which we haven't really studied very well, about to what extent the Indian groundwater economy is following Hartwick's rule. We do find some evidence that endowment with more groundwater resources associated with more accumulation of both asset and human capital today. There are many limitations to the study. There remains identification challenges. We only look at one type of channel through which these investments might have taken place. And we have nothing to say about whether in terms of quantity, those amounts of accumulation are sufficient to keep the economy on this weekly sustainable trajectory, just whether there is an association at this point. Thanks very much.
Wonderful. That's right on time. Thank you, Ram. So we are open to questions. I think I already see some questions here in the chat. Leah Babies has a question about Ram. I would love to know the source of the map of the alluvial aquifers on the right. I guess that's more of a data question.
So I do have another couple of questions if I could add more substantial questions. Thanks, Ram. That was really interesting. I'm Leah. I'm at Ohio State University. I have two sort of broad conceptual questions about like just sort of how you're conceptualizing this project, which I think is a really interesting question. The first is that like you're looking at human capital levels, which is certainly a measure of sort of how people are transferring this groundwater to sort of direct day-to-day wealth. I really agree with that. That's interesting. But if we think about economies that have successfully transferred from a resource extraction economy to a non-resource extraction common, I'm thinking sort of places like Scandinavia going from like cod fishing to, more complex economies. I feel like, something more is needed, right? Like you don't just need healthy people, you need to invest in a industry or, factories, or, you need to invest in a very specific type of education, right? So I'm not sure I think what you're showing is interesting, but I'm not sure I buy its connection to this sort of larger idea of like transitioning from an extractive economy to a non-resource extractive economy. Though that's not so much you're doing it wrong. Like it's just sort of an interesting, it's still an interesting framing. And the other thought I had is that you're showing within basically sort of places around the Indo-Gangetic Plain that being closer to being on alluvials is associated with higher height. And yet we also see that India-wide, the northern Indo-Gangetic Plain is the place that's had the least movement in height over time, right? Like it's actually sort of in a way like people will frame it as a resource curse, right? Like people are sort of stuck in poor health there and poverty over a long period of time. So in a way, you're showing a sort of micro level association that I almost feel like is flipped on the larger level, which I think is interesting and maybe also comes back to this idea of how people transfer wealth in a complex way that I'm not entirely sure I can articulate beautifully at the moment. Yeah, very thought-provoking. Thanks.
Yeah, I totally agree with you that I think I agree with you that it's going to take more than these household level investment to transition the labor force in the same way. So I think the best we can say is maybe there is a contribution here that how important that household level contribution is to that transition is hard to say. That's a good point. So we're not claiming that it's the only driver of this transition, but maybe it plays some role in it through these household level investments. And the same goes for the point about health in the Indo-Gangetic Plain. So we are only comparing people in the same district, both are basically in the same overall area, who have or do not have groundwater. And I think it's the fact that this low level of health persists in those areas is probably not because they have groundwater, right? So there are probably other reasons for that. And all we are saying is that within that area, with everything else that's going on, if you have groundwater, maybe you've been able to increase your height relative to those who don't, to some extent, right? So just to clarify that.
Yeah.
That I agree on both counts.
There are two more questions in the chat. Do you want me to read them? Or
yeah,
I mean, Leslie, we can unmute and ask yourself if you want.
Oh, I see a question on the map. It's available for purchase. Anybody who wants it can contact me. Just kidding. It's on the Central Groundwater Board website, for example. I think you can find those maps. They're very easy to find. There are actually even much more detailed maps than that are available there. So we only use a very coarse divider, but you can find something that's much more granular also. Leslie, to your question, we focus on not alluvial aquifers, but we focus on districts that part of which has alluvial aquifers and the other part does not have alluvial. And the reason is because alluvial aquifers just have a lot more water stored in them and they're easier to extract. When it comes to other types of aquifers, it's more subtle. So we decided to go for the very, very coarse division of alluvial versus non-alluvial, because there it's very clear that you can get more water more easily. Whether it's happening because of Paddy or not, I'm not sure. It could be one of the channels.
Okay, I think we are out of time. Maybe you can respond to Suhina in the chat.
Yes, India's different ethnic groups. Right, so we control forecasts, for example, and the other types of information that we have in the DHS in all of these regressions. I'm sure that they play a very large role as well.
Yeah, okay, thank you, Ram. Thank you for the interesting, thought-provoking presentation. I do have some questions for you, but I'll ask another time. So now we are in the final presentation discussion. Soumya is over to you now. So we're looking forward to hear your points on these three presentations plus other overarching comments.
It's very hard to be the last act when there are three really good presentations out there. So let's see what I can do here. If I can, yeah. Okay. Yeah. Let me know what you see. Yeah, can you see this?
Not in the presentation. Now it is, yes.
Okay. Great. Okay, so I'm going to make a sort of think about this as a set of questions that I've been pondering on. And I think it would be great for people out there who are interested in this problem to go and think about this and see whether there's opportunities for you to answer some of these questions, either theoretically or empirically, especially empirically, because the answers to some of these questions are likely to vary across space considerably. And through this, I'm going to kind of touch upon the three presentations that we've seen as well. And I'm deliberately calling it slowing down the problem, because I don't know what the word sustainability means from an operational perspective. So I think we all agree that, there's a lot of groundwater extraction in South Asia. It may have done lots of good things, but it's also something that somehow needs to be addressed. And, the two things that we keep thinking about in the context of addressing these problems are pricing and technology. And I'm going to talk a little bit about what I think are the knowledge gaps in these two realms that need to be addressed comprehensively for any meaningful and feasible policy-related dialogue to have, because I come from a world where I think about research for policy or for implementation, research for policy or research for implementation and programming. And of course, needless to say, all opinions are mine. They don't belong to my employer, and any errors are also mine. And of course, I believe that no idea is unique. And if I'm thinking about it, there are lots of other people who've been thinking about it. And so I'm grateful to a number of people whom I've had a chat with as I was writing and conceptualizing this work. So I'm going to say that both the thinking about water energy pricing, and I'll use the term water energy pricing interchangeably, because in the context of groundwater, you need energy to pull it out. So the role of pricing and the role of technology, both of them have a role to play in slowing this problem down. But we need some policy-oriented research to fill these knowledge gaps. And on the pricing front, the big question is, if water were to be priced, or prices on water were to be increased, water and energy were to be increased, what would the welfare implications of such an increase be? And more importantly, how would that welfare implications be distributed across the population? Specifically, would it be regressive? And this is kind of the work that Disha is kind of thinking about. On the technology front, there are a number of technologies, irrigation technologies, that could improve efficiency. Things like direct seeding of rice, alternate wet and drying, ostensibly even drip irrigation that could be used in certain places. But heterogeneity, uninsured risk, and labor shortages are likely to be significant barriers in the adoption of these technologies. And so to what extent these are barriers and how can these barriers be eased is going to be an important knowledge gap. And I don't think enough is being done to think about it. But more importantly, if we look at the literature on pricing and technology, they do sometimes tend to be quite disjoint. And I think that pricing and technology are two sides of the same coin. In part because prices increase incentives to adopt technologies. You have no incentive to increase efficiency in irrigation if you don't pay anything for water or energy, or you pay very little for water and energy. But however, if pricing water and energy, or increasing prices of water and energy, does will increase production costs, then all the more we need technologies that improve efficiency that might bring some of those costs down. And so thinking about the two of them together is also something that we need to increasingly do. And I would like to argue for an observatory approach because it's likely that the effects of pricing and technology are likely to be heterogeneous and variable. And so I would like to argue for an observatory approach using microeconometrics and research and collaboration between research and policymakers. Let me talk quickly about water pricing and what I think are some of the knowledge gaps out there. This is based on work which is in review. And it's really quite simple. If you look at the 5 countries in South Asia, while the share of agriculture in GDP has steadily fallen over the last 40 years or so, at the moment, the share of agriculture in GDP in any of these South Asian countries is not really more than 22%. Its share in employment is still very high. Going up as high as 62-63% in Nepal, and even in Sri Lanka, which is the lowest, the share of GDP in agriculture is, I think, below 10%, but in employment, it's around 25%. And this is going to be important for thinking about welfare implications, because it also seems that not only is the share of employment in agriculture high, relatively poorer people tend to be disproportionately employed in agriculture. So when we think about water pricing, we have to think about water pricing as having private and social considerations. We've thought about this on the supply side, where we talk about the marginal cost of the private marginal cost of irrigating, but then there are all these externalities, especially environmental externalities to irrigating, and those environmental externalities have received considerable attention in the literature. But the point is that water pricing also has private and social considerations on the demand side. So not only is there a private marginal revenue from irrigating, obviously, there are also what we might call societal objectives that we want to achieve. And these are beyond just incomes of irrigators. And some of our speakers have spoken, both Ram and Marie Charlotte's work has spoken about this today, where societal objectives, particularly on the demand side, are things such as local food security that might be achieved through dietary diversity or even consumption smoothing. So even when dietary diversity is not achieved, just the availability of food locally goes up, prices smoothen down. And there is extensive literature on how irrigation contributes to local food security through these channels. Irrigation also provides significant employment to local labor, both on farm, but also off farm. And there are multiple uses of irrigation water, not only for livestock, but also for bulk household use. And these aspects are rarely raised in the water pricing literature. And so this is important because, this is a very simple, marginal cost, marginal revenue, private social setup that we're all familiar with. It's kind of the 101 of microeconomics theory. We assume that if we were to price water, we would be moving from QP to QR in quantity. But in reality, we're probably moving from QM to QS. And the relative differences between these two movements is going to depend on the relative gap between the private and social supply and the private and social demand and the elasticity of the demand curve. And this kind of goes back to Keith's question on, on Disha's presentation on when prices for water go up, not only is water use going down, but other inputs are going down as well. So the welfare effects of these changes of increasing prices on water or electricity will depend on the elasticities of demands for the products in question. So if you think about staples like wheat and rice, the demand for water is highly elastic. So it typically results in reduction in use of inputs and reduction in use in food production. For high value crops such as vegetables and horticultural crops, which are fairly inelastic demand for water, it results in reductions in cultivators' incomes, ceteris paribus. Now, both reductions in quantity of product produced, as well as reductions in income, will have other knockout effects. So labor use may fall. It'll affect consumption smoothing and crop choices. And the ability of, and just the local economy effects are going to be fairly significant. And so the question then becomes, how do you leave the farmer no worse off if you were to increase prices on water? And this is sort of speaking to the question that Disha was trying to answer. But the point is that the effects are not just going to be on the cultivator. There will be effects on people who don't cultivate but provide farm income, and on other local economy effects as well. The other thing that's missing in the literature is whether water pricing would disrupt informal water markets. And so informal water markets are quite ubiquitous in South Asia. So usually the well owner sells water to marginal farmers around them who don't have their own pumps and wells. And these informal groundwater markets serve many farmers and cover vast areas. Older estimates exist. Newer estimates are not quite there. And part of the problem is that IGMs or informal groundwater markets are very rarely systematically studied, in part because of data gaps. So for example, the minor irrigation census in India, which happens every 10 years, there's an agricultural sample survey which happens every 5 years that collect a lot of information on input use, but neither of these data collection activities really asks questions on whether farmers are buying or selling water. The one study that really looks at the systematic looks at IGMs through a sample survey is J.B. Meenakshi and Abhijit Banerjee's paper in JDE. And it's a great paper. Please go look at that. There is work that Marie Charlotte has done in West Bengal that sort of looks at when costs of supplying water are lowered, smaller, by which we mean people who don't have pumps but have smaller land holding sizes tend to get served. And so, lowering the cost of irrigation can very much have these pro-poor benefits. This is a nice paper in JDS. Please go look at it. So what we don't know is if we were to, in the presence of informal groundwater markets, if water and energy pricing were to be distributed, would well owners shift their dues to water buyers? Would they reduce supply to water buyers? And what would these welfare effects look like, and for whom is just not known. And that needs to be understood fairly well in order to have a meaningful conversation on pricing. The other thing that people have been thinking about is, hey, you can't price electricity and water because it's always been free in South Asia. It's politically contentious. It's expensive and messy to do. Maybe we can provide positive incentives. So introduce an opportunity cost for pumping. So one way to do it is to assign electricity entitlements, which would mean metering farmers who have sort of not been metered so far, and buy back unused units. So the idea is that you don't pay for water and electricity, but you have an entitlement of electricity. And if you don't use your entire entitlement, you can still make some money because you sell it back to the utility. Now, can this work or not? There are two case studies, both of them in India. One is in Punjab. This is a paper that I've had the privilege to write with my PhD student, Fishman Mitra. It does work in the case of Punjab, but there are caveats to kind of scaling it. And the other paper that experiments with this is a paper that came even before our paper. This is Ram's paper in Gujarat, where the assignment of electricity entitlements with an opportunity to sell electricity back to the utility does not really change pumping behaviors at all. And the difference between these two seems to be that in Gujarat, people share wells, and there's also an extensive informal groundwater market as compared to Punjab, where Disha rightfully said, everybody has their own pump. Every plot on every farm has its own pump, and there are really no informal water markets. But even in cases where, like in Punjab, where it might work, it's not clear whether this is cost effective to do it at a larger scale. For one, entitlement programs such as these seem to work when farmers know when the electricity is going to come, which is daytime, usually in India, because electricity is provided free of charge or is highly subsidized. The supply of electricity is rotational, so farmers really don't know when the electricity is going to come. So if it's coming in the middle of the night, are you going to step out and turn on your pump, turn off your pump? Nobody really knows that. We also don't know that if these programs were to be introduced in places like Gujarat or other places in India where there are informal groundwater markets, what are the consequences for tenants who don't own their land but rent land, and water buyers who might have their own land but don't have their own water source? What are those welfare consequences going to be like? And what is just the cost of implementing these programs, which are fairly complex to implement, compared to any discernible impact that we might have on either subsidies or groundwater? That's something that we don't understand at scale. And this goes to the implementation costs of these kinds of programs, both directly pricing water or indirectly sort of introducing some sort of an opportunity cost. The incentives to manage water use are greater when you move towards volumetric pricing, but that's also the direction in which transaction costs of implementing programs in a geography where nothing of this sort has ever been done are also going to be very high. And so we don't really understand this practically enough to be able to make these decisions at scale. When it comes to irrigation technologies, the first thing I'd like to talk about is some of the information gaps in solar irrigation. And so broadly, there are kind of two ways to solarize irrigation, if you will. One is what we call a standalone solar pump. So think of it as a small pump that's powered by solar panels, and you can pull water out of the ground. The reason why standalone solar pumps are very attractive from a government's perspective is because it's a way of converting a perpetual variable cost subsidy on electricity, to a one-time fixed cost subsidy on basically a capital cost subsidy. So as farmers, as irrigation needs to expand, including in South Asia, governments might find it attractive to simply move from perpetually subsidizing energy to actually just giving people solar pumps. So that may be an actual economic advantage to the government, or a fiscal advantage to the government of doing so. Now, because the marginal cost of pumping in solar irrigation is zero, it's not surprising that solar pumping will increase incomes, production, and groundwater extraction. And there are a bunch of papers that empirically study this, including Kashi's paper that's just recently come out in ERL. And so policy sort of makers are a bit concerned about, we can expand energy use by changing the nature of the subsidy. That's fiscally very attractive, but are we kind of exacerbating the groundwater problem? And so some people are thinking about geographic suitability of these standalone pumps. Is there, could sensors be put? I mean, most pumps these days come with sensors. So could you enable these sensors to at least monitor how much of water is being extracted? Might it be possible to use sensor technology in order to, in some way, regulate the amount of water that people pull out? Though this might be highly inefficient to do so because of extreme heterogeneity between farmers on, what's the optimal amount of water they should be using. So these are fairly complex questions. And so there's some thinking around that front. The other way to solarize is grid-connected pumps. And so the idea of a grid-connected pump is essentially you have a pump that's essentially powered by the electric grid. You also install solar panels on the farm, and the solar panels produce electricity and evacuate it to the grid. And so the farmer is charged on a net metering basis, and there's a difference in the price the farmer pays when they draw electricity versus the price that they get for the electricity that they sell. So there's some kind of incentive at the margin. It's a fairly complex engineering exercise. It's not easy to implement them. There is one grid-connected solar pilot, if you will, in Gujarat. And the claim there is, well, could you incentivize the farmer to make rational decisions at the margin on pumping versus selling electricity, and incentivizing them to kind of look at the opportunity costs between the two. It's not clear how large the incentives need to be, or how large the tariff, the feed-in tariff, the price at which the electricity is bought, needs to be for this to be an effective incentive. And again, in the presence of informal groundwater markets, if there are opportunities to make extensive margin changes, what's going to happen? So there's a whole bunch of questions that we don't understand about this that also need to be looked into.
So we only have about a few minutes left in the webinar things.
Sure. So drip irrigation, sort of, without the Jevons paradox, essentially, drip irrigation increases irrigation efficiency, but typically also leads to changes in the extensive margin. More land comes under irrigation, crop type changes, or people add an extra crop, etc. This was the economic theory has talked about it for a while. Ram's paper in JDE experimentally looks at this and finds exactly the same. But the question is, can you use drip irrigation effectively in areas where there is no extensive margin, or the extensive margin is maxed out? So can you use this in places like Punjab and where every inch of land is already cultivated and irrigated with wheat and rice? There is some interesting work that the Ram and his colleagues are doing out there, trying to look at whether this is feasible. The problem with using drip with wheat and rice is it increases weeding. It also have to lay down the drip lines every season. So is labor shortage, likely to be a barrier? And what implications might this have for some kind of downstream water use? Because drip irrigation essentially reduces recharge of groundwater. Other technologies such as alternate wet and drying, direct seeding of rice, things that are supposed to make you maintain the yield of water, or maintain rice yield, but yet reduce the amount of water that you need to apply into the field. The biggest challenge that seems to be in adoption of these technologies at scale is heterogeneity. So while the farmer experiments with these technologies on their yield, generic extension advisory needs to be tried and tested in the field in order to have field-specific use. And in that interim period of trial and error, there could be a yield penalty. And so part of it is how do you end up modifying extension to be more village-specific than generic? And also, if there's going to be a yield penalty in the point that period experiment with these technologies, do you need some kind of bridge safety net programs, like some kind of cash for work programs bundled with AWD while people experiment with it? And of course, both AWD and DRS might reduce water application, but they also increase weeding, which is laborious and an expensive task to do. So in the net, what do production costs kind of look like in the event you were paying for water, but had to pay more for labor as well? And that needs to be understood as well. And finally, it's really about bringing these two pieces of empirical literature together. So there's this very interesting work that Ujjain Chakravarti and others have come out with, where they look at, is the adoption of technology itself better when prices are there? And they find that is the case. There's other work that Ram and colleagues and some of us at the bank are doing to kind of try and understand this intersection between pricing and technology, and how does that change behaviors for farmers. Do these technologies reduce total production costs? So what if they reduce water and energy use but increase labor? And so in the net, what does that look like? And can technologies themselves disrupt informal groundwater markets? So for example, Ram's paper that looks at drip irrigation in Telangana, it's Andhra Pradesh, maybe I can't remember which one. They talk about how drip irrigation also helps increases water sales to neighboring farmers. But Ujjain's work in Bangladesh finds exactly the opposite, where introduction of AWD actually reduces water sales, and we can talk a little bit about what those channels are. So in short, we need better data. Like I said, we have sample surveys and irrigation census that don't seem to collect data on informal groundwater markets. There's really a gap out there for people like me who work with government in order to kind of fill that gap in and finance that so that this can be done. But there's tremendous scope for people who are thinking about small sample studies, to think about using non-randomized studies as to study barriers to adoption, risk aversion, looking at proof of concept of ideas, thinking about randomized studies, to think about pathways at which treatment affects. And for policy recommendations, which is really about where do you put your money, we are going to need large sample surveys simply because heterogeneity is absolutely the bane of policy. But going beyond just one aspect and thinking about the trade-offs between what do these kinds of interventions do for water use, farmer profits, employment, and just the distributional consequences of these policies, some of which might be regressive, and also unintended consequences. Thanks.
All right, thank you very much, Soumya. So we're already actually over time, so it's already 2 minutes over the time. But I'm happy to stick around and take maybe take a few questions. Hopefully, other speakers are also willing to do that. If people have questions, people unmute yourself and ask questions. We're happy to stick around a few minutes.
I have a question. This is Suhina Diol at Oklahoma State University. So I'm working with irrigators in Oklahoma, Texas, and Kansas that are using the Ogallala Aquifer and doing groundwater irrigation. And there's, a huge, there's big property rights. And, there's a huge issue with monitoring, like Kansas has done it, but folks in Texas and Oklahoma do not like being monitored, and it kind of goes against our groundwater law. And water is not priced, and it's very cheap. So we're running on a lot of those things. But one program that we're kind of looking more into, and we're also trying to figure things out and run larger surveys, is we have the EQIP program with that's a Farm Bill Helps Fund, which it's like where we have farmers who are irrigating, we pay them instead, like, hey, switch your crop to a less water intensive crop. Hey, do dryland farming this year. And, we're trying to do more surveys on like who's participating and what they would like to see more. And I'm kind of wondering, is that something that you've looked into, and have there been any programs that have looked into, like, the biggest thing that comes to my mind whenever I hear about this is like in Punjab, we don't grow rice and people are turning their fields into rice fields, which is just crazy. And so it's like, well, why not just pay these farmers to grow wheat instead? So could you kind of help, comment on that? Because like for us right here, like we would have an uproar. Like we're not gonna have farmers pay for water. I mean, like that would just be insane, And so it's like, yes, pricing incentives work, but like that's not going to work. Like it's not going to work because it's not practical. So yeah, would you like to comment on that?
Sure. I think it's a great question. So I think the scope for doing this is going to vary drastically. So for example, the Chinese are paying farmers money to keep their field fallow in the winter season and not grow the winter crop, simply because the value of that water is in the North China Plain. And the value of that water, it's very valuable for domestic and industrial use, right? So the value from farmers not cultivating at all and that water instead being used elsewhere is in the net a huge benefit for the Chinese economy. In Punjab, we could in principle tell farmers not to pay and give them tons of money. The problem is it's not clear where in that time, there is no other use for water that's as quote unquote valuable as agriculture is. So in a sense, if you're going to be paying farmers in Punjab to not cultivate, they're getting money to not cultivate, and they can keep cultivating for longer periods of time because that water is still going to be in agriculture. So I think the whether you should do it or not, I think is going to vary considerably across space. In some geographies, it may make sense. It may make economic sense to do so. And in other geographies, it's just, you're just putting more money into the hands of the same people who've, contributed to. And again, let's be careful about what we mean by contributing to the problem, because as Ram's work is showing, irrigation actually does a lot of things. I mean, the one thing about, say, for example, India is there may be a lot of groundwater use, but if the monsoons fail, we won't have a famine. And so again, what we mean by the problem is also a bit of a tricky thing. But in terms of paying farmers to not do stuff or keeping land fallow or changing crop type, makes sense to do it in some places, may not make sense to do it in others.
Thank you, Samir. Can I have Disha say something about this?
Yeah, just to add a little bit to that. So thank you, Sahina, for your question, your query, and your suggestion on that. There is actually a crop diversification scheme that's, there are, cash incentives being offered in Haryana, and they're also announced in Punjab. And although, I do see that there are some blog posts and articles on that, we're still, working on writing a paper on the same. So just to, give you a gist of what we really find out, whatever cash incentive the government is, first of all, thinking of paying to the farmers, that's really not sufficient enough to give an incentive to the farmers to shift away from paddy into some less water intensive crops, just because the paddy yields are way, way higher than these less water intensive crops. And also the cost of cultivation is different, and there is a market risk and a production risk also attached to cultivating these less water intensive crops. So there are overall a lot of differences, and it's not just about paying some cash transfers to the farmers in order to change their behavior. There's a lot more that's going on in the background in order to deal with it. But yeah, one of the ways could definitely be having some incentives. But on the other hand, there has to be, sustainability in terms of for how long do you want to offer these cash incentives, and it can't go on forever. It has to be sustainable within the system. Yeah. Thanks, Kashi.
Yeah, let me just comment, so for us, they apply for so many years and we give it to them. And I'm not as familiar with the issues going on in South Asia. That's why I'm here. But it's I guess I don't understand, because okay, if the farmers aren't using the water, right? There's plenty of people in the city, higher value activities for bathing and all these other things, right? That we need to do. So I guess that's where I'm lost, right? We can move this water to higher value activities.
Yeah,
yeah, I think it depends on where you are. So for example, there isn't a problem for people to access water for livestock, bathing, or domestic purposes generally in Punjab. So, and the biggest sort of commercial activity out of water in Punjab is agriculture. So in the Punjab context, the economics just doesn't add up.
Okay, thank you.
It's really as simple as that. In the China context, the North China Plain is really adjacent to Beijing and the larger metropolitan area. And so you want that water, and there's this industrialization which is happening. And you would rather want to divert the water there than have it in agriculture. So the Chinese are paying farmers twice or thrice the amount they might have made from cultivation. Because it makes sense for them to do so in the larger. I mean, keep in mind that, a bunch of idle farmers getting lots of money, cash in hands, creates social problems of its own. And, I spent 2 years working with the Chinese on this, the North China Plain, and they will privately tell you that it has other kinds of challenges, but the economics of it is not a challenge there. So I think there's an economic angle to it, and then there is a social angle to it, and both of them are going to be important, equally important considerations in policy.
Yes, well, there is indeed a whole political economy behind that on the transfer of water use. And taking the case of Solfegia, we are talking of millions of wells. So there is also just a regulatory framework behind that. No one knows how to monitor who is using the water and how much water is being used by which user. So that's also the actual setup that we work with.
Ram, you want to respond to this question that's been ongoing?
Yeah, I think all the major points have already been said, so I don't have much to add. I think also I think it could make sense in a lot of contexts, because I think near cities, like there are, especially if you think about the electricity which goes into this irrigation, I'm sure that there are a lot of industrial and domestic users which would love to be able to tell a farmer, hey, you're getting it for free. Why don't I give you 3 rupees and I'll get it instead of paying 6 rupees to the utility? For sure. But I think the main challenge here is how to institutionally make that possible. I think it would be great if it could be made possible institutionally somehow. The transaction cost may be very high. This is what we learned also from Samia's work in Punjab, but if that could be implemented, I think I'd love to see what would happen.
All right, thank you. I guess we don't have time. We already have almost 15 minutes over. So thank you, everybody. I think we're already losing people. So thank you, everybody, for joining this call. And thank you to amazing presenters for sharing your thoughts. So this is actually a great turnout. I'm super happy about this. Thank you again. And we'll see you somewhere in our next.
Thank you so much.
Yeah.
Thanks a lot, Kashi. Thanks for organizing.
Thank you. My pleasure.
Thank
you,
you.
everybody.
Thanks.
Bye. Ciao.